All right, so we want to take a look at a reaction mechanism. So all a reaction mechanism is just a proposal of a possible pathway for a reaction. Okay, we're going to add them together just like we would a Hess's law problem. Okay, so we have to identify intermediates in the problem, get rid of them, add together the different steps. They call them elementary reactions here. Okay, they're the same thing, just like the Hess's law. You know, you had like 2 or 3 or 4 steps that you added together. Those smaller reactions are elementary reactions. Okay, and they use some extra vocabulary here. Try not to get too confused with it. So they call them elementary steps. Okay, and then they actually ask about like the molecularity of the elementary step is like it's just dumb vocabulary that you have to be aware of. Okay, that makes it doesn't. It's just fanciness. Okay, okay. If it's unimolecular, there's one reactant. If it's bimolecular for its molecularity, there's 2 reactants. Or, could be 2 of the same reactants. Okay, that's bimolecular. All right, and if it's termolecular, there's 3 reactants there. All right. Now, one thing I would say is termolecular. This is one of the questions on the reading guide. It's very rare because you have all 3 things colliding in the proper orientation with enough energy of activation. It's hard enough for 2 things to collide with each other with both those caveats, right, with collision theory. All right. So it's very rare because 3 reactants must collide in proper orientation and with enough energy of activation. Okay, so just understand that you'll see that vocabulary. It's going to be asked of you. All right, so be aware of it. It's not overly difficult or anything. You just got to remember what they're asking for when they're talking about molecularity or an elementary steps and things like that. So the best way to take a look at that would be like a sample problem like this. So we have this overall reaction with hydrogen and nitrogen monoxide giving us nitrogen and water. And they're saying, okay, well, here's a possible mechanism for it, these 3 steps. All right, so I'm just going to label them. So the steps, just so they're easier to talk about, 1, 2, and 3. Okay, and they want to know, okay, what is the molecularity of each of the 3 steps? All right, well, if I look at step 1, in step 1, what's its molecularity? Yeah, it's bi, okay? Bimolecular, because there are 2 NOs there. Okay. In number 2, there's an NO2 or N2O2 and a hydrogen. Bimolecular. Okay. In step 3, there's N2O and hydrogen gas. Oh, that's bimolecular as well. Okay. Now they also want to have us show that the sum of these elementary steps is the net reaction. Okay, so just like Hess's law, the steps got to add together to just look like the picture on the box, right? The overall reaction. So we have to add all the steps together to get the overall reaction here. So what do we need to do? Cross out our intermediates. Okay, what are intermediates? What's that? Right, yeah, the products of one reaction that are used as reactants in another. Excellent. Okay, so what would be an example, Matt Lee? What's an example of an intermediate for this? For these? So wait, so tell me what substance am I looking for? N2, N2O, great example. Yeah, N2O is produced in one reaction and then consumed in another. Yes. N2O2 is another one. Good job, Israel. Boom. Okay. So when you add this together, we end up getting 2NO plus 2H2 going to N2 and 2 waters. Do they match? Hey, all right, check. We got it. All right. Okay. All right. So, a couple things that I want to highlight here for you is when we go and we start doing these, one thing that you need to understand is ultimately the reaction, the rate law expression can only be determined experimentally. Okay. The mechanism is just a proposed possible steps in reaction. Okay, so those are just possibly these are the steps that the reaction takes to get to the finish line. Okay, but ultimately the rate law needs to be determined experimentally. Okay, because the slowest step in our mechanism is also the rate determining step. That ultimately is going to give us the rate law expression. So you're hoping that they match. You're hoping that the slowest step and above in our mechanism match our rate law determined experimentally, which we did either using the integrated rate law method or the differential rate law method. Okay, where you use the table logic and stuff. All right, comparing data. You got to use data. All right. So we talked about reaction intermediate, produced in one step, consumed in another. The catalyst. Okay, the catalyst. I want to kind of clean this up a little bit. It goes in as a reactant. Okay, and the first reaction it comes out unchanged. And it's not listed about it comes out unchanged in the final reaction. Okay, so it goes in as a reactant, comes out as a product, unchanged. Okay, unchanged. That's a catalyst. Okay, and we'll practice those a little bit. Some steps for determining whether a reaction mechanism is valid or not. Okay, so we're just we'll take you through these here, and we'll double check to make sure. We'll do a couple examples here to work through these here a little bit. Okay. All right. So in this example here, we've got our overall reaction between nitrogen dioxide and fluorine, and they're saying experimentally the rate law is rate is equal to K times concentration of nitrogen dioxide times concentration of fluorine. What's the overall order for this reaction? Second order. How do I know it's second order overall? Yeah. Yeah, these are the first, right? So overall order is equal to 2, right? And you got to add the exponents together. Okay, so they're saying, hey, here's a mechanism that's been suggested. It's got steps. The first step is a slow step. The second step is the fast one. Okay, and pretty much every single one of these types of problems will be identified. One of those steps is going to be marked as slow. The rest will be fast. Okay? So they want to know, is this mechanism acceptable? So in order to figure that out, so first thing that we need to do is we need to add the reactions together and check to see if they match the overall reaction. So do they match the overall reaction? Okay, that's kind of the first question. So we got to add them together. Okay, cancel out our intermediates, right? Fluorine is gone. And then it should be 2NO2 plus F2 going to 2NO2F. Do they match? Yeah, they do. They match. Okay. Check. All right. So that's so far so good. All right. Secondly, the rate law needs to come from the slow step and above. And I'll talk about what above means here in 1 second. Okay, so does the rate law that they've determined experimentally match the rate law in our slow step of our reaction here? Okay, so if we look for at the rate law in this guy, right, we are only looking at reactants. Okay, so our rate law expression would be rate equals K times concentration of NO times concentration of F2. That's that. Okay, so in this case, the rate law is possible from the quote-unquote slow step. Ultimately, yes, this is acceptable. So sure, this will work, but we don't know if that's the exact. You can always say like, hey, this is proposed. It works. Maybe this is it. Okay. And in the next problem, I'll show you what I mean by the slow step and above. So we'll include any reactions above the slow rate determining step of the reaction. Okay. The amounts of reactants in those steps above in the slow step and above are going to matter for us for the rate law. Okay, so there's that one. So let's do the next one here. We'll keep going here. All right, so can you guys find some intermediates in these two reactions? What's an intermediate here? It's got to be produced in one and consumed by another. Check Barkat. IO. Okay, that is definitely an intermediate. Okay, it's produced in one and consumed in another. What about a catalyst? An example of a catalyst here. It's not an intermediate, but a catalyst. Yeah. Again, minus. Catalyst. Okay. Goes in as a reactant. Comes out as a product. Unchanged. Okay, it's unchanged. It goes in as an I, comes out as an I. Done. Okay. Doesn't matter what happens to it in between, just as long as it goes in as a reactant and comes out as a product, and see how they're identical. Okay, good. All right, so that would be an example of a catalyst. Any questions about that? All right, it is not produced or by one of the reactions. The intermediate is produced by one of the reactions and consumed by another. All right, so what's write the balance equation for the overall reaction? So add them together, get rid of reactants or get rid of intermediates and catalysts when you add it together. You add it together and get rid of the intermediates and the catalysts for the reaction.
Two H2O2 and two H2O
Plus O2. Great. Okay. So there we go. So they want us to write the rate law for this mechanism as well. Okay, they want us to write the rate law for this. So what we need to do, the rate law is from the slow. We need to look at the reactants in slow step and above. Okay, but you're going to ignore intermediates. Okay, you want to ignore intermediates. So if we have the slow step, we want to look at the slow step and above. We need to get rid of intermediates. Okay, so when we go ahead and we write the rate law for this, so rate is going to be equal to K times the concentration of H2O2, hydrogen peroxide, squared times concentration of iodine. Sir. Okay, so see how IO was made by one of the reactions, right? And then it was used up in another one. The I just go, you have it to start. Okay, the I is one of the original reactants to start. That's why it's not and that's why it's not intermediate. Everybody see where the 2 comes from here? Okay, we got 2 H2O2s. That's why we add them together. That's how we're getting the order to be 2. Yes. Correct. H2O is not involved. Yeah, we don't care about the products. Only look at the reactant side. Only look at the reactant side. And then on the reactant side, make sure you ignore intermediates. Okay. All right. So what if, though, the rate law actually was, if the first step was the slow step, when we go to write the rate law, let's say this step is the slow one. How is that going to change our rate law expression here? Yeah. Great. There you go. Yeah, it's only to the first order for hydrogen peroxide, not second. If the first step was the slow step, because it's the slow step and above. Okay, and there happens to be nothing above this, but it's only the slow step we would look at, so it's just H2O2 and iodine. Okay. Okay. All right. Let's move on to 1990 here. Decade that you guys miss, unfortunately. That's too bad. Some of you guys born in 99? Oh!
There's some kids at school that born.
Well, see, you know, I became officially old when all the kids I was teaching were born after the year I graduated high school. That's when I was like, all right, I'm old now. I'm old. All right. 97. 97 when I graduated high school. I was only 17.
Go to high school.
No, I had a real young birthday. Yeah. So, yeah. What's that? Oh, yeah. Yeah.
Where'd you go to high school?
Sandburg High School. All right. So here we go. We got A and B going to C and D. Okay. Delta H is negative 10. So what kind of reaction is this knowing the delta H is negative 10? Exothermic. Good. Okay. Exothermic. Good. I'm so happy with exothermic. All right. All right. So, or you can use that as a good pickup line there, people. All right. Of course they want. Right? Right? It's good stuff. All right. In the science building at college, it'll work. Okay. All right. So describe the two factors that determine whether a collision between molecules A and B result in a reaction. So remember, collision theory, right? What are the two things necessary for a reaction to happen? Okay. Got to collide with proper orientation. And what else, Maggie? Yeah, and enough activation energy. Yeah. Enough energy of activation, right? Enough activation energy. All right, so how does a decrease in temperature affect the rate of the reaction, right? A decrease in temperature would affect the equilibrium too, but we only care about the rate for right now. So how would the rate be affected? Definitely is. It would slow down. Why? Yeah, slow down. So there's straight up. There's just fewer collisions, right? I mean, you can even talk about, well, there's less energy. The particles moving less kinetic energy, so there's not as much energy around to reach energy of activation. I mean, you can go on and on there, but ultimately, what it boils down to is there's just going to be less collisions. Period. Particles moving slower, less collisions, less reactions. Okay. All right. Rate law expression. Write the rate law expression that would result if the reaction proceed by this mechanism below. All right. So if we look at this, our slow step is right here. So our second step is the slow step. So we got to look at the slow step and above, right? Cross out any intermediates. And then write our rate expression, our rate law expression from that. Everybody see where that's coming from, right? We have an A in the reactants. We have two B's and an A. Yes. So that would be, well, this would be the rate law would be third order.
Yeah.
But if you look at each individual step, you would look at for molecularity. So this would be bimolecular, and this one is going to be bimolecular as well. Termolecular, all three have to be written in the same reaction. Okay, so that would be like A plus 2B going. You know what I mean? Okay. Excuse me. So what is a catalyst? How does it increase the rate of the reaction? Yep. Yeah. Lowers activation energy. Okay, needed for a reaction to occur. So more collisions results in a reaction. Now the key part here is they're asking for like equilibrium constant. Look, we haven't gotten to equilibrium. Next, that's going to be our next unit coming up, right? The reason why equilibrium doesn't change because the reverse reaction is also the energy of activation is lower for it as well. So you just reach equilibrium faster. But the amount in the end of, remember, equilibrium is a relationship of products, the amount of products divided by the amount of reactants. So it's the ratio between those. In the end, the ratio will be the same. You just reach equilibrium faster. Okay? And that sort of thing. There are also two types of catalysts, right? There's an adsorption catalyst and an absorption catalyst. Okay, so the adsorption is one where the catalyst, the reaction takes place on the surface. Okay, and the absorption is where it gets absorbed and goes internal, and the catalyst happens to do the work inside it. Okay, like the catalytic converter in your car, I believe, is an absorption one. The gases go through the catalyst, and inside the catalyst is when it helps the reaction happen. Okay, where silica would be an example of an adsorption one, where it's on the surface of the silica and how it reacts and helps the reaction happen. All right. 1996, my junior year of high school. Yep. I think I weighed like 100 and, I don't know, 30 pounds maybe. I didn't really grow until my junior year. I didn't really grow much. I was little, yeah. My freshman year, I was about I think it was 4'11", 90. I was 95 pounds freshman year. I wrestled my freshman year. I was wrestling in the 103 weight class, but they also had a 98 pound that I could qualify for as well. And I didn't have to lose any weight or anything either. So yeah. So I didn't grow till later. So oh yeah, I didn't really. I was growing through freshman year and stuff as well. Yeah, I didn't reach my full height until like end of freshman year of college, beginning of sophomore year. That was really when I was like still. After that point, my shoes didn't change sizing. You know what I mean? Like I had to continually. All right. All right. So write a balanced equation for the reaction. Okay. Overall reaction. Write a balanced equation for that. You can do that. Make it happen. Oh, I'll take you to a link actually to solve that problem. But we're going to do the first part to help you with the differential rate law. All right, is everybody through A and B? Start to work on C. Okay, so good. So C is telling us that, all right, a student says, hey, the rate law for this reaction rate is equal to K times nitrogen monoxide squared times concentration of hydrogen gas. Okay, great. The student then concludes that, number one, the reaction is third order. Okay, is it third order? Yes, it is, right? 2 plus 1 gives us 3. So number one, sure, that's good. That is correct. Okay. Number 2, they say the mechanism involves the simultaneous collision of 2 N2 molecules and an H2 molecule. And they ask, okay, are conclusions 1 and 2 correct? So number 1 we already said is good. Yeah, sure, it's third order. Check. Yes. It's just 1 H2.
Oh, okay.
We got to look at the don't get confused with that. That's the overall reaction, but the rate expression that they have is like, hey, this is it. That's it. All right. All right. So, according to their mechanism, do 2 NOs, N and H all collide at once? No. Look at it. 2 NOs collide, and then the H collides in with that afterwards, right? It happens in two different steps. So their second postulate there is no good, right? That's not correct. NOs collide first, then the H2 in the next step. Okay, and notice where the rate loss coming from here that the student got. See where the slow step is here? So we look slow and look up above, right? Notice what we got here. 2 NOs and an H. That's where the rate law is coming from, not the overall balanced equation. Okay, the rate law is coming from the slow step and above. All right, slow step and above, and that matches right here, right? 2 NOs and an H. There we go. We go with that? Okay. All right. Part D here, explain why an increase in temperature increases the rate constant K. So what's the deal? Why is an increase in temperature increase rate? What? More collisions. Yep. Yeah, more collisions, and you can even argue like, okay, the kinetic energy of molecules is higher. So more collisions have energy evacuation for a reaction. Okay. So not only will you get more collisions, but more of the collisions will even result in reactions because you got molecules colliding with more energy. Okay. So you got enough energy for the energy evacuation there. All right, so let's look at this next problem from 1984 about working a differential rate law problem where you have a problem in terms of, so first of all, when you look at this problem, what do you notice? Rate, concentration, concentration, right? That should scream at you. That should scream at you differential rate law. All right, that should scream at you differential rate law. And you're going to be using, right, this is the one where we solve it table logic wise. Right, we use table logic to solve this. Right, okay. The other type is when you have time and concentration. Then you break out your calculator. Okay, and use your plot the data on your calculator and go. All right, integrated rate law. Those are only two options. That's it. Okay, two types of problems. All right, so if I see this, and I look at these, I want to use table logic, right? I'm just looking at this. I'm like, okay, concentration of X is the same here in this first count in reaction 2 and 3 here, right? So I can ignore X and just look at these and be like, okay, 1.4 goes to 1.8, right? That's doubled, right? What happens here? 0.2 to 0.4, that's doubled. Okay, so what does that tell us about Y, the order of reaction for Y? It's first order, right? Okay, so we know Y is first order. Okay, we know Y is first order because you double concentration, rate double. Okay, rate double. All right, now we need to find Y, a couple reactions where Y has the same concentration. There are none. Oh no, like what do I do now? Okay, no problem. You can work this out. Okay, you can work this out. So all I'm going to do here is I'm going to take the first, I'm just going to label these 1, 2, 3, 4. Doesn't really matter which one you choose now, okay? But I'm just going to take, I don't know, we could take the middle two still. Let's just go with the middle two. Okay, we'll go with the middle two. All right. So when I set this up, and I like to work with like, well, it doesn't really matter, whole numbers. Okay. So I'm going to take reaction 3 and put it over reaction 2. Okay. So basically, I have the rate of reaction 3, so 2.8 times 10 to the minus 3 over 1.4 times 10 to the minus 3, and that's equal to K. And for reaction 3, it is 0.4 raised to some power X, right? I don't know what the order is with respect to X, okay? And I got 0.4 raised to the first power, right? Over 0.4 raised to some power X, and 0.2 raised to the first order, the first power. A's cancel out, right? 0.8 times 10 to the minus 3 divided by 1.4 times 10 to the minus 3. 2. Okay? 0.4 divided by 0.4 is what? 1, right? So it's 1 raised to some X power. Okay? 0.4 divided by 0.2. It's 2, right? Raised to the first power, which is just 2, right? Okay? So 2 divided by 2 gives you 1 is equal to 1 to the power. Equals 0. Be 1. So I kind of screwed this up. We picked the wrong numbers. Yeah. What? You could also still use table logic here and look at this. Right? See these? See these? Right? I know that this doubled and this doubled has to be attributed to Y, because we know that for sure. Well, this went up. That has 0 effect.
If we only did that and we didn't like show like reaction 0, reaction 2, or do you want that too?
I think actually, if I would have chose any other reaction combo except this one, it would have worked out actually well. Because these are 1, this is 2. That would have ended up with 2 raised to some power X. It gives you 1, right? This and this is 3 to some power X raised to 1. You know. What's up?
I'm just showing you guys how to take a line if you pull up and double. You know from why if you double that, the reaction will double. And I don't get from there from
So like if I know that if I double this, the reaction rate should double. Well, if I look at this doubled, but the reaction rate only doubled, so I know that this had no effect then, right? That's the other way you can just use table logic. Because otherwise, what should we have seen? If that concentration doubled, and we notice that this went up by a factor of 4, then we could be like, oh, that's first order and first order.
I just did my math.
Oh, I got you. Yeah.
I'm not afraid. Wait.
I did. Well, the only thing is with that is it was nothing new. You know what I'm saying? So, but yeah, what are we gonna do about that?
So when could I do that?
I would do it as soon as possible. So what does that mean? When can you make it happen?
I have a study hall right now.
You want to do it right now? All right. Integrated rate law. Plug it in your calculator. Figure out which one it is. Go from there. Let's just work right over here. Yeah, let's do it. I'll get it to you in 1 second.
How does that success for you? Great. Right? Let's go down. Question?
That, that's not, okay, you said it was the hardest one yet, right? I did the best on it. Like, what's my best? I'm like,
Yeah, that's a good average to keep up to. That's keep being hard, you get better.
yeah. My grade went up by 2 whole.
I bought one.
No.